So let's move on with the higher order partial derivatives. Of course, when we do have these higher order derivatives in normal differentiation, so of course we also have higher order for partial derivatives. And the thing is, you can express this as easy as it looks in this expression. Now, if you want to take the higher order, for example, this one is the partial derivative of z with respect to x. And then whatever is the answer, if you try to take the partial derivative of that with respect to x, then you will be getting this expression. And that's already the higher order derivative. But unlike the higher order derivatives in normal differentiation, wherein we're just like differentiating with respect to the same variable over and over again. But in this case, because we are talking about this multivariable calculus Euclidean geometry, we know very well that x, y, z can be the plane of our equation, and then we can have variables more than 2. So with this case, we can see that higher order derivatives can also occur when you try to differentiate first the expression with respect to y, and then the second one you differentiate this with respect to x. That's why this is z, y, x, meaning you differentiate the expression first with y and then followed by x. The same goes for f sub yx, so the function should be differentiated with respect to y and then with respect to x. Okay. Now, there's a theorem that says that if we have a function that is defined on a disk D, and the functions f sub xy and then f sub yx are continuous, then the derivative of f with respect to x followed by y at the same point is equal to the derivative of the same function with respect to y and then x. So that simply means that you can just see that if we have differentiated this expression in terms of x and then y, that will be equal to y, the derivative of the function with respect to y and then with x. So what can be concluded here is that you can interchange this expression. But how about if we try to have something like a third derivative? So what we have is something like x, and then y. So with this, you can also express this in terms of f and then y, x. That should always be the same. Or you could also have f and then x and then y and then x. You can always interchange the order of the differentiation as long as you have the same differentiating variable in any case. So if you have two x's here and then y, so you should always have the same for the other expression. No matter the order is, for as long as you have the same differentiating variables, then you would still get the same answer. So let's try doing this. So for this equation, we need to find the derivative with respect to x. So that's the second order derivative, partial derivative. And then this one is the third order derivative with respect to y. So let's just use this in another sheet. Okay, so let's do this one. We need to take the partial derivative of z with respect to x in this expression. So we have z sub x. Now, this can also be expressed in terms of z sub x sub x. So, first, we need to find z sub x. So, that is equal to 2xy for the first term. And then we have here, since x is a constant, 2y squared is a constant, so we have minus 2y squared. And then x would be equal to 1. And then we have plus 1 over x plus y. And then the derivative of x is 1. Y would be 0. So this is the first derivative with respect to x, partial derivative. And then for the second derivative, partial derivative, so we need to differentiate this with respect to x again. So we'll be left with 2y here because x is just just x without an exponent. And then this one is 0, but this one becomes plus. We know that this can be rewritten as if it's x plus y raised to negative 1. So with that, we differentiate this. So that's negative 1 times x plus y raised to negative 2, and then the derivative of x plus y is simply 1 plus 0. So that is 1. So finally, our answer for the second derivative of partial derivative of z with respect to x is 2y minus 1 over x plus y, and then that is quantity squared. Okay, so this is our final answer for the second derivative of z with respect to x. Now, how about this expression, finding the expression with respect to the third derivative with respect to y. So we first take z sub y, that is equal to x squared, and then minus, we know that this is actually 2y, so that becomes 4xy. Okay, and then we have plus 1 over x plus y. And then for z sub y, that is, this becomes 0, and then this one becomes negative 4x. Okay, and then we have a minus x plus y raised to negative 2, because that's the same thing as what happened here. It's just that we're differentiating with respect to y. Okay, so this is the expression in terms of c sub y, and then finally we need to take the third derivative with respect to y. So we have 0, and then this one is negative times negative 2, and then we have x plus y raised to negative 3. So with this, z sub y is equal to 2 times x plus y raised to negative 3, or that's 2 over x plus y. You can also write this as 2 over x plus y, then cube. Okay, so with this is our final answer. Okay, so that's just a pretty simple example. Now let's have another one. Now for this example, we have a lot. So we start with f sub s sub s. So that is the second partial derivative of u with respect to s. So this should be u, but because we're thinking f as if it's the function given, so we'll be using this e to the negative 3s as if it's f is equal to u. So we take f sub s, or this is also equal to u sub s. So we take e raised to negative 3s, so that's e raised to negative 3s, and then the derivative of negative 3s is negative 3, and then we have minus 7, and then the derivative of hyperbolic tangent is secant h squared. So whenever you see something like a hyperbolic function and you need to square that, you put the exponent to the upper portion of h instead of putting that on the upper portion of c, because that only means that you're actually taking the secant squared of h. So that's not the case. You're actually taking the hyperbolic squared of the secant of s sub t. So you put 2 at the top of h. So we have negative 7 secant h st. So we need to differentiate st. So with this we have only t, because we're differentiating with respect to s. Okay, so with this we know that u sub s is equal to negative 3 e raised to negative 3s, and then minus 7t. Oops. So we have minus 7t, and then we have secant h squared, and then st. Okay, now we proceed with u sub s, so that is equal to negative 3 e raised to negative 3s, and then we multiply this with negative 3 again, so minus, now 7t is a constant, so we have 7t, and then the derivative of secant h squared of s of t is, we'll be using power rule first, so we have 2, and then secant h of st times the derivative of secant ht, which is equal to secant h st, and then tangent h st, and that is actually negative because we're taking the reciprocal function in this case. So we also multiply this with the derivative of st, so that's equal to t. Okay, so that is our derivative. So with this, u sub s is actually equal to positive 9 e raised to negative 3s, then that is minus, so that's 14t, and then we have secant h, that's squared, st, and then we have tangent h of st. Oh, we also have t here, so we squared this expression. I also have to make this positive because we have negative, and we also have negative here. Okay, so that's positive. So now we proceed with the third, and this tallies with the answer 9 e raised to negative 3s, and then plus 14t squared, secant h squared st, then tangent h st. Okay, so we proceed with u sub ts. So we know that we differentiate this with respect to t first and then s. But you can also do st because according to Clairaut's theorem, that should always get, that should be giving you the same answer. But for the sake of correct mathematical order, let's just do u sub t and then u sub t sub s for this expression. So for u sub t, so with this we have u sub t is equal to, this becomes 0, and then this one is negative 7 secant h squared again, and then that is st, but this time the derivative of st is now s because we're differentiating with respect to t. And then u sub t will be simplifying, we have negative 7s times secant h squared of st. And then if we need to take the derivative with respect to s for this expression, we know quite well that this becomes product rule. So we have negative 7, so we do product rule, s times the derivative of this secant h squared st, so that's 2 secant h and then st. Then the derivative of secant is actually negative secant h st tangent h st, and then the derivative of st is simply s. T, because we're differentiating with respect to t. With respect to s. Okay. So plus, we have secant h squared st, and then the derivative of s is simply 1. Okay. So with this, our final answer, u sub ts, is equal to, now I think we can factor out secant h squared in this expression. So that's negative 7 secant h squared and then st. So we're left now with, this becomes 2s, negative 2s tangent. So we have negative 2s tangent h of st. Oh, we also have t here. So that's 2st, I think. So we also have plus 1. Okay, because that's secant h squared st. Okay, so I think, let's check the answer, negative secant h squared st. Okay, and then we have 1 minus 2 st, okay, tangent h st. So that's the same. Okay, and then finally, oh, it's not yet the final question. What we have here is the second partial derivative of f with respect to t. So we already obtained the first one here. So that's u sub t. We also have, so from this, I'll be just continuing this with respect to t. So u sub t is equal to, this one is a constant, negative 7s. So that will just be copied. So negative 7s and then times 2 and then secant h, that's st, times negative secant h of st, then tangent h st, and then the derivative of st with respect to t would be s. So that is u sub t, that is equal to negative or positive 7s squared, 14, that should be 14. So we have 14 s squared secant h squared st, and then tangent h of st. Okay, so that is our answer for u sub t sub t. I hope you can follow through with our differentiation process. So whenever you get confused with the derivative, just look at the rules. You'll be able to understand it more. So let's check if the answer is correct. Okay, so I think this one is incorrect. I don't know where did I get this answer. But the correct answer is this one, 14s squared secant h squared st tangent h st. Okay, so now you proceed with this u sub t sub s. So what we have here is, we just start with u sub t sub s, because I think we already obtained the correct answer from this one. So we just continue this expression that we have here. So with this, we have u sub t sub s. Let me check again if that's u sub t sub. Okay, so we have u sub t sub s. So we need to differentiate this expression with respect to s. And in this case, let me distribute the terms first so that it will be a lot easier for us. So with this, we have positive 14. We have positive 14 st. And then we have secant h cube, I think. Not cube. So that would be squared st and then tangent h of st. Okay. So I think that's all for the first term. Okay, I hope I'm not missing anything. So we have minus 7 secant h squared and then st. Okay. So with this, I can now differentiate this further. Actually, this should be u sub t sub s only because I'm not yet differentiating. Okay. And now it can be u sub t sub s that is equal to, now for this one, because we have something like st secant h squared st tangent h st, so this is something like three expressions that we have multiplied together altogether. So we know that when we do product rule, we'll be doing this product rule twice. So let's just do 14st. So I'll be distributing 14st with the whole term. So that will be 14st. And then the derivative of this using product rule. And that's the product rule on the inside. So we have secant h squared of st. The derivative of tangent h st is simply secant h squared st times t, because we're differentiating with respect to s. And then by product rule, we know that that is plus tangent h of st times the derivative of secant h squared s. So that's 2 secant h of st. And then the derivative of secant h is actually negative secant h st. And then we're run out of space. So we have, I think I should be moving this one with, let's move the expression here. This one. Somewhere here. Okay. So I'm differentiating the secant, so we have tangent h of st. Okay. So, and then the derivative of st is also positive t. Okay, so that's it for the product rule of this expression. That is actually in the product rule of 14st, or with this whole expression on the outside. So I would have to add this secant h squared of st tangent h of st, and then I need to multiply this with the derivative of 14st, so that will be 14t, because I'm differentiating with respect to s. Okay, so that's for the first term. Now for the second term, we have minus, so we have 14 secant h. We've been through this for quite a lot of time. So we have times secant or negative secant h of st tangent h of st, and then times t. Okay, so with this is your answer. We just need to like simplify this. Okay, so we have 14st Okay, so I think that's the simplest expression that I can give you. So let's check that on our answer. Okay, so with this, let's box this as our final answer. And then let's have another. So this one is our final, I think, final example for higher order partial derivatives. So what we need to do here is to prove that u sub t sub s is equal to u sub s sub t based on Clairaut's theorem. Because according to him, or to them, I don't know, if you have this kind of expression, and whenever the differentiating variable is just interchanged, you can just get the same result. So we first do u sub t, and in this expression, we know that we already obtained this u sub t. Actually, we already have u sub t sub s. So this is the answer. Let's just copy this so that we can minimize the process. And then I think we also have u sub s, and hopefully we can obtain the same result when we try to do it. Okay, so this one is the expression for u sub s. Now let's try to proceed with the process, and we know very well that for this to happen, we need to differentiate this first expression with respect to s, so that it becomes u sub d sub s. That is equal to, so this one is the one I'm doing. So we need to differentiate this with respect to s, so that is, I don't know if it's, I think this is correct. This is already the u sub d sub s, so I don't have to do it anymore. But so let's delete this one. Now I will just have to do it for this expression. So we have to do u sub s sub t. Okay, and in this way, I need to differentiate this with respect to t. So I know quite well that this one is product rule because this has t, and then this also has a t on the inside. So we get negative 7t times the derivative, so that's 2 secant h of st, then times negative secant h of st, and then tangent h of st, and then the derivative with respect to t would be s. Okay, and then we have plus, because it's product rule, so we have secant h squared, then st, times the derivative of negative 70, so that's negative 7. Okay, now let's try to simplify this further. So we have u sub s sub t is equal to, that will be positive, I think, positive 14 st secant h squared st, and then tangent h st. Okay, and then for this one, we also have, I think that's positive, or negative 7 secant h squared, and then st. Okay, so now that we have this one, we can factor out 7, I think 7 secant h squared st, so that we'll obtain the same pattern. So with this, we have already distributed negative 7, so we have positive 1 because this is the expression itself, then minus because that becomes positive, so minus, I think that will be 2, and then st tangent h of st. Okay, so with this, if we will be comparing this u sub t sub s, and then this one is u sub s sub t, so they're just the same. Remember, this one is positive 1, and then this is minus, so we have positive 1 and then minus 2 st. So with this, we have already proven that u sub t sub s is the same as u sub s sub t based on Clairaut's theorem that we know. So I think that's all for these higher order partial derivatives.